Okay, I want to tell you about a few interesting predictions of the general theory of relativity. One of those has implication for effectively everyday life now. It turns out that if certain things predicted by general theory of relativity are not taken into account when a GPS system is designed that you might have on your smartphone, it wouldn't work properly. Okay? So general theory of relativity is not something that sort of is out there that is understood and only by a small group of highly trained cosmologists, but its implications are relevant now for everyday life. So let me discuss two of those. So important results of the general theory of relativity. I said that basically the essence of this theory is that it's geometrical in a way. The way the gravity works is that a mass bends space and time because the two are intrinsically coupled, and then objects move in that curved space along the paths of shortest distance, so-called geodesics. Okay? So it turns out that the following two things are also predicted. First, so-called gravitational redshift. Okay, so what it is suppose that I have a body of mass m, and let us have a source of blue light next to it. So it emits photons or electromagnetic radiation at the wavelengths corresponding to the blue light. But as these photons are moving away from the source of gravitational force, they're losing the energy. And remember, the energy of the photon is inversely proportional to the wavelength. So as the energy is reduced, the wavelength grows. So after a while, it will become a green, and after a while, it will become red. Right? So as the photon escapes the gravitational pull by mass m, it loses energy, and as a result, the wavelength of light increases. And that is because the photon energy is given as a ratio of some universal constant, which is the product of Planck's constant and the speed of light. You don't need to know all these details, so I have a constant over the wavelength. Okay, so as the photon moves away, it loses energy, and as a result, the wavelength increases. As the energy is reduced, that means that is equivalent to saying that the wavelength increases. Now, what I've drawn here is, of course, exaggerated. I mean, in principle, this exists even in the case of light that I shine from, say, a flashlight into the sky. As those photons escape the gravitational pull of the Earth, their wavelength, in principle, also increases for the same reason. Okay? However, the mass of the Earth is not that great compared, say, to a neutron star, right? Or a black hole, a massive black hole. So that increase in wavelength resulting from the photon escaping the Earth's gravity is tiny, okay? But it's there. And people have actually measured it. But it's much more pronounced, this increase in wavelength from, say, blue to red, if the source is near a very massive object, such as a dense neutron star or a massive black hole. Now, this type of redshift is different from what we discussed in Astronomy 1P01, the redshift caused by so-called Doppler effect, which is the increase in wavelength when the source of light is moving away from the observer. Okay? So this is totally different physical reason for the redshift. As you will see when we start talking about the cosmology, there is a third type of redshift, so-called cosmological redshift. And that has to do with the constant expansion of the universe. As the universe is expanding, imagine you have a surface of a balloon, right? And you draw a wavy line on the surface of the balloon. As you put in more air, as the size of this two-dimensional universe, which is the surface of the sphere, increases, what will happen to that wave that you drew, it will get stretched. The wavelength, the distance between two successive crests or troughs, will be increasing as the space is expanding. Okay, so that's yet another type of redshift, but we'll talk about that one later. But please do not confuse this gravitational redshift with the one caused by the Doppler effect. Okay, the second prediction is that the stronger the force of gravity, the slower the clocks run. And this is, of course, quite general. So again, we have a body of mass m, right? It could be our Earth, it could be a star like Sun, it could be a neutron star or a black hole. And this would be the event horizon of a black hole, the boundary. And say I have two clocks, right, at different distance from this body. And the closer the object is to this body, the more curved the space is, or the stronger the force of gravity. So the force of gravity on this clock here is stronger than the force of gravity on the one that is at a greater distance from the body of mass m. So say that this clock here shows 3 o'clock. Then this one that experiences a stronger force of gravity would be actually late. It would be showing, say, 10 to 3. And yet, initially, before they were brought near this mass, they were synchronized. That is, they showed the same time. So the one that is experiencing a stronger force of gravity runs slower. And as I mentioned, these effects need to be taken into account when the clocks are put on satellites that are part of GPS system. So the relativistic effects, both of special theory of relativity, GPS stands for, so how does it work? This is the Earth, and there are altogether 24 GPS satellites, and they are at an altitude of about 20,000 kilometers above the surface of the Earth. And they move at the speed of 14,000 kilometers per second, per hour, sorry. And they are distributed such that from any given point on Earth, 4 are visible, but usually more, right? So, because they are at the altitude of 20,000 kilometers, they experience a smaller force of gravity than at the surface of the Earth. And therefore, it turns out, when you do the calculation, it turns out that the clocks on the satellites run by 45 microseconds faster than the clocks on the Earth. 1 microsecond is 10 to the minus 6 seconds. And this is effect of general relativity, as we've just mentioned. Now, because the satellites are moving at fairly decent speed, 14,000 kilometers per hour, the special theory of relativity tells us that the clocks, because they are moving relative to us with this speed, should run by 7 microseconds slower. And this of course, faster per day. So the mismatch is 45 microseconds per day, 7 microseconds slower. Okay, and this is prediction of special relativity. So the net time difference between the clock on the satellite and the ground clock is 45 minus 7. They run 38 microseconds too fast. Okay, so you can say, well, I mean, this is nothing, right? 45 times 1 millionth of a second per whole day, that's nothing. But not so. The speed of light is very fast. The way this works is as follows. The satellites are constantly sending signals, and the signal contains the information when the signal was sent according to the clock on the satellite. The GPS receives that signal and knows the time when it arrived. So from the difference between the two times, when the signal was emitted and when it was received, we know how long it traveled, we know the time, we know that the speed with which it was moving, which is the speed of light, and therefore we can calculate the distance to that particular satellite. And if we know the distances to at least 4 satellites in 3-dimensional space, then we can actually pinpoint the location of a person on the Earth. So is this a time difference of 38 microseconds really important? It is, because the speed of light is 300,000 kilometers per second, or another way to view it is 1 foot per nanosecond. Okay, so the speed of light is about 1 foot per nanosecond. Right, and 1 nanosecond is 10 to the minus 9 seconds. And we have in 1 microsecond, we have 1,000 nanoseconds. So then the distance the light travels in 38 microseconds is, I have 38 microseconds, which is 3,800 nanoseconds. So this is the same thing as, 38,000 nanoseconds, which is the same thing as 38 microseconds, times 1 foot per nanosecond per day, and that is 38,000 feet per day. And that is about 11 kilometers per day. Okay? So if you didn't take into account these relativistic effects, after 1 day, your distances would be wrong by 11 kilometers. Just after 1 day. Okay? So what was done was that actually the atomic clocks on the satellites were slowed down so that there was no mismatch of 38 microseconds between the clocks on the satellites and the ground clocks. And that's why the GPS can work, you can use it on your smartphone or the GPS in the car to locate your position and the direction of motion with a great accuracy. Okay? So general relativity is something that has effect on our everyday lives at the present time with the current technology, right? And this whole thing would not work. Can you imagine the air traffic if there was an error of 10 kilometers per day in locating the planes, right? It would be a chaos out there.